So on 1.5, we're talking about continuity, and we have this graphus interruptus again that we looked at in the previous section. This weekend I went and I kind of redid most of the worksheets and notes, so we don't run into this problem, but there are some missing symbols here, and hopefully they're fixed. There should be an epsilon, and that should be negative infinity to infinity. All right, so we're looking over the entire set of real numbers. So very quickly it says, on that interval, from negative infinity to infinity, list the largest intervals to which the function is continuous. So it's kind of like what we did on the previous example, and it's just practicing from left to right whether we can include the left to right endpoint, and of course we have to stop and step over any interior discontinuity. So with the arrows there, you can kind of just assume that it's going to be continuous off the visible graph. So as we come in on the left, we can come in at negative infinity. And we can cruise all the way up to the first discontinuity, which is at x equals what? Negative 2, there's a vertical asymptote. Now notice the function's defined at negative 2. There's a dot there. It's right here. It eluded some people last time. But can we include negative 2 as an endpoint? No. So it gets a wimpy parenthesis. And then we step over it, and we start on the other side of negative 2, and then we cruise to the next discontinuity, which is at what? Positive 2. And can we include 2 as a right endpoint? No, we can't. It's kind of open there, so go to 2. And then union, we step over 2. And then we cruise to the next discontinuity. So now 2 is a left side, and again, it's open, so I already threw it down there, sorry. It would be a parenthesis. And then we cruise all the way up to what? 5. And because of the vertical asymptote, we can't include it. And on the other side of 5 now, the vertical asymptote's there again, so we have another parenthesis. And then we cruise to what? Bless you? 6. Now, can we include 6 as a right endpoint? Yes, there's a solid dot there. Good. Union, when we step on the other side of 6 now, we're on this little interval, so can I include 6 also as a left endpoint? No. So it would look like this, and then it would look like that. So we can go from 6 to 8, it looks like, with another open. So parentheses, 6, 8, parentheses. And then the next one would be from 8 to 10. And again, those are both open. So a lot of open intervals here. And then on the other side of 10, we go from 10 to, yeah, not far at all, 10 to 11. And it's open on both sides. You're never going to have to do something quite this many. And then once we get past 11, which we can't include as a left endpoint, then we can keep going forever. So infinity, and of course infinity always gets a parenthesis. Bless you. So really the most interesting transition, bless you, was at 6, where we could include 6 as a right endpoint, but not as the left endpoint. So that function is continuous on that interval. Is that also the domain of the function? No, it's not. It's not the domain of the function. Because notice here at negative 2, we have a function value, but it's not continuous there. At 2, we have a function value, but it's not included on either side. Same thing at 8. We have 2 open intervals, but it's not included. And those are really the only places. So you got to be careful. A function can have a discontinuity and still be in the domain of the function. And we'll talk about that later on in this section. Okay, so part B. These now kind of work their way nicely into what would be like a multiple choice question. On the same graph, find the largest value of B such that the function is continuous from 5 non-inclusive up to B inclusive, but not continuous from 5 to B plus 1. So basically, if I start at 5, I want to find the largest value of B so that it works when I include B, but as soon as I add 1 to the upper bound, I want it to fail at the right endpoint. I want it to fail, not be continuous when I add 1 to it. So the first thing you want to do is look at where we're starting. We're starting at 5, so let's come up here. 5 is where this vertical asymptote is, right in there. So would 5.5 work for my B value? Yeah, because it would be continuous from 5 to 5.5 included. But when I add 1 to 5.5, it takes me to 6.5. And that's going to fail because it's taken me past the what? What type of discontinuity do we have at 6? A jump. So essentially, anytime I add 1, if it gets me past 6, now it's going to be non-continuous on the open interval because it's going to span the jump. So 5.5 would certainly work. But is that the largest value? No. Would 5.8 work? Yeah, because it would be continuous from 5 to 5.8 inclusive. But now when I add 1, it takes me to 6.8, and it fails for the same reason. What about 5.1? Would 5.1 work? Yep, because when I add 1, I get 6.1. So there's a lot of different values that it could be, but what would be the largest value that works? 6. Good. So the answer to this question is 6. Because it would be continuous from 5 to 6, that would work, but then it would fail from 5 to 7. Because, again, the jump at 6. So B would be the answer to the largest value of B, but now it says to list all the possible values of B that work. Well, all the possible values of B that it could be. Now, if 6 is the upper bound, we're going to list it as an inequality rather than interval notation, because this is where it gets confusing. We're talking about a solution set now for intervals. So B can be 6, and we know it can be smaller than 6 so long as it's greater than what? Has to be greater than 5. Okay, it can't be 5, but it can be any number to the right of 5. 5.00001 will work because when you add 1 to it, you add 6.001 and you span the jump. So any value of B in that interval will work for this right here. Now, this is where it gets confusing. We're not saying that the function is continuous from 5 non-inclusive to 6. That's just the values of B that make this scenario happen, okay? Go ahead then and try out C on your own. It says to give the smallest value of A so that the function is continuous on the largest possible interval from A non-inclusive up to 10. So to make the interval as large as possible, since A is a left bound, we want A to be as small as possible. And then it says what other values could it be? While y'all are doing that, I'm going to come up here to the graph and kind of rewrite the questions because it's easier to see when the graph is here. Anyone get it? 8? You think it's 8? So you're saying that the largest interval with 10 as an upper bound would be 8. So that would be the interval from 8 to 10, which would be here up to here. Yep, I totally agree with you. Because when we let the left bound equal 8, I cannot include 8, but notice it's not saying we have to. There's a parenthesis around A. That gives you the largest interval from 8 to 10. So now that we know that A is the smallest value that gives you the largest interval, what other values of A will work? Well, we know A can equal 8, obviously, right? So I know it could be greater than or equal to 8, so long as it's what? Strictly less than 10. Yeah. So any value now of A between 8 and not up to 10, but like 9.9, it's going to be continuous from that number up to 10. So from 9.9 to 10, 9.99 to 10, 8.1 to 10, that's going to work. So again, the interval is from A to 10. This inequality down here gives you all the values that work. All right, so the next one is part D. Find the smallest value of K so that the function is continuous on the open interval from K to infinity. While you're doing that, I'm going to grab all this stuff up here, shrink it down, and then relocate it to the proper letter. K to infinity, smallest K. What is it? 11, not 10? It's not continuous from 10 to infinity? No, it can't because there's a jump at 11. So 11 would be the smallest value of K that works, which would make the interval as large as possible. Okay, so now that we've answered that, that's the smallest K that works. Are there other K values that would work? Yeah, like 11.1 would work, right? Would 11,000,000.1 work? Yeah. So any k value that is what in relation to 11 would work? Yeah, greater than or equal to. So k could be any value greater than or equal to 11, so long as it's still less than infinity, right? Okay. Last one. Find the smallest value of k so that the function is continuous from k inclusive to infinity. Now we want to include it. What's the smallest value of k so that it's continuous from k inclusive up to infinity? Would 11,000,000.1 still work? Yeah. Would 11.1 still work? Yep. But we want the smallest value of k. So how about 11.01? Does that work? Yeah, 11.01 would certainly work because it's to the right of 11 where there's a dot, and I can include it, but it's certainly not the smallest. So it would have to be a number that's between 11 and 11.01. Like 11.001? Yes. Could you do like k minus 1 over infinity? Good thinking. Right. You can't do that because infinity is not a number. But here's what we can do. If we could somehow, so we can't let it be 11, right? Because there's no way I can include 11. It's an open circle. So as long as we can just list the first real number after 11, that'll be the number we want, right? What is the first real number after 11 on the number line? That would be the first real integer or whole number or natural number after 11. But the first real number, the very next number. No, you can get as close as you want. Like we can say 11 point, and for the rest of the year go around and go, come back the next day. Where do we leave off? With okay, all year long, right? And then it's time for school to end. We got summer, and the last person on the way out the door says 1. Well, that's a number really, really close to 11, right? But is that the closest one? No. In fact, we're still infinitely far away. So there is no first real number after 11. There is none. So what can we say? No such k exists. And if this were a multiple choice question, then of course that would be one of the answers. You'd have like A, B, and C being like actual numbers, and then choice D would be no such value of k exists. So it's an option you have. That's the answer? That is the answer. Yeah, there's no such k, so that you make the interval as large as possible. There is no smallest k, and that's what it said, smallest k. There are infinitely many values of k that work, so that this is true, but there is no smallest value, like there was above. No, because the only value that works is the first real number after 11, and there is no such thing. Okay? I'll show you a little magic trick, right, where you pick two numbers, then you cut it in half, right, and so now there's this much size. Then you zoom in, then you cut it in half, and then you zoom in and cut it in half, and you zoom in and cut it in half. You can keep doing that forever, right? Forever, right? And maybe you put weights in between, a little resistance, and you get a workout while you're at it. I don't know. You have to eat sometime. All right. You like those types of questions? They're not that difficult, but they do require a little bit of thinking, and they make great multiple choice questions. All right, so shifting gears here a little bit. Continuity is a very, 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 very important property of functions, because functions that are continuous then can be used to answer like real-life questions when we model equations around the real-life behavior. So here is a non-comprehensive but pretty good little box that includes some functions that are continuous over their domains. Over their domains. Now, is every function continuous over their domain? No. I mean, we have examples like piecewise examples like this at x equals c. X equals c is in the domain because there's a dot up there, but it's not continuous there. Or we have like a jump discontinuity or something like that, where it's not continuous at c, but yet c is still in the domain. Or we even saw at Graphus Interruptus, remember the vertical asymptote? With that sneaky little defined point on the vertical asymptote? Okay, this would be a discontinuity, but still in the domain. So not every function is continuous over their domain, but everything in this box is. All right, so let's go ahead and read it. Hey, there's Coach. Let's tell him a pirate joke. What is a pirate's favorite type of shorts to wear that he incidentally can't wear to the school? Cargo shorts. Cargo shorts. Yeah, there you go. There you go. Very good. Very good. All right. So, polynomials are continuous over their domain. Rational functions, those are like polynomials over polynomials. Root functions like cube root of x, square root of x, all your trig functions, sine, cosine, tangent, secant, cosecant, cotangent, they are all continuous over their domains.
Wait, but don't,
I'm not saying their domains are all real numbers.
no, like how cotangent is like this, and it's like this, like the vertical asymptotes are. Wouldn't that be continuous?
Yes, but vertical asymptotes are actually not in the domain of the function. So what we're saying in this chart is if the graph exists, it's going to be continuous there. The graph doesn't even exist at a vertical asymptote. So I'm not saying these are the functions that have domains of all real numbers. I'm just saying over their domains, where they exist, they're continuous. Some of these have vertical asymptotes, right? So in between the vertical asymptotes, it's going to be continuous, all right? In other words, you don't have something like this, a vertical asymptote with a dot on it. But sine and cosine are especially of interest. Inverse trig functions, especially arctangent, exponential functions, and log functions, okay? Now notice the ones with the asterisks here. Does asterisk mean like we have to make note of that because they were playing in the steroid era, and so we have to put an asterisk by their home run record? Is that what that means? No. No, but that's what happened when Mark McGuire and Sammy Sosa were going after Roger Maris's record, home run record, right? That was in the juice step period. But, you know, usually if there's an asterisk by something, there's usually a legend underneath it that tells you what the asterisk means. Like, asterisk right here. The functions with an asterisk use steroids. No, it doesn't say that. It says the functions with the asterisk are continuous for all real numbers. So those are especially important, right? So where are polynomials continuous? Not just over their domains, but all real numbers, because that's their domain. So they're continuous everywhere. Are rational functions continuous everywhere? No, they might have holes and they might have VAs, but in between those they're continuous. But sine and cosine are continuous where? All real numbers everywhere. Arctangent, all real numbers. And you know what that one looks like, right? That's the one with the, yeah, you all got it now. And then exponential functions are continuous everywhere. Cool. So why is it important to know where a function is continuous? We've already talked about it a little bit. First of all, if we had to evaluate their limit and we knew they were continuous, what do you know about continuous functions and their limits and their function values? What's that? Oh, if it's all real numbers, then they'll go out forever. Yeah. But if we know a function is continuous at a point, what do we know about its function value and its limit value? They're equal to each other. They're the same. So we can evaluate the limit by finding the function value. That's kind of important. We've already talked about that. But here's another important application. By combining continuous functions in an algebraic way, adding them, subtracting them, multiplying or dividing them, or even composing them, putting one inside the other, we can create brand new functions that are also continuous over their domains. Oh, okay. So I can just take two continuous functions and kind of mush them together and get another continuous function over its domain. So that's what we're going to be doing on example 4. It says, give the intervals for which the following functions are continuous, and I give you the secret of how to do it by finding their domains. So it becomes now the exact same task. If I gave you this function h of x and I said, what's the domain of the function? It'd be the same thing as asking you over what values of x is this function continuous. Why? Because I took two continuous functions, x squared and sine of x, and I combined them to create a new function. But this is not multiplication, this is what? When you plug one inside another? Composition. So this is like sine of x squared. All right, so let's find the domain. How do we do that? Anyone? How do we find domains of functions? Without graphing it, we have to do it up here. Yeah, so to see if there's any values that don't work, right? So let's start on the inside, like if we were actually to evaluate it. We'd start right here, right? Pick an x. Are we free to choose any x we want? Sure, yeah. And then I square it. Is that going to give me an output? Yeah, so what's the domain essentially of x squared? All real numbers. Now the outputs of x squared, also known as the range, those become the inputs or the domain for sign, right? So what is the output for x squared? If I square a number, I'm only going to have what types of numbers? Positive, or at the very least, 0, right? Can I take the sign of any positive number or the sign of 0 without any problems? The sign of any positive number would be a positive radian angle. And what's the domain of sign? All real numbers. So I could take the sign of any positive number, 0, and negative numbers. Just so happens I'm not going to find the negative numbers. So if it passes both for all real numbers, guess what the domain is? All real numbers. So d sub h, that's how you can write it. The domain for the function h, colon, is double bar R. Wow, that is just a coincidence that I was able to say that on the day like today. Double bar R. That's like double fire talk.
And then we get to write.
Oh, I'm sorry, back to math. Yes, sir, sorry. That's okay.
We get to write after that h of x continuous over all our numbers.
Yes, good question. Because have we really answered the specific question that was being asked? No. It didn't ask us explicitly to find the domain. It said, see if it's continuous by finding the domain. Whoa, hey, there I am. So here we go. Come on. Okay, so, great transitional word. So, h of x is continuous. Yeah. You could do this for all x in the set of real numbers. That's a beautiful way to do it. Okay, did y'all hear what I said when I wrote the upside down A? For all, yeah, and it's a real symbol. It's a set notational symbol. For all x in the set of real numbers. That means for all x. Good. Thank you, Anthony, for keeping us on task. Okay, so the next one. Take 1 minute, size it up, chew on it yourself, and I'll meet you back here in a minute and we'll talk about it and see if you can get it. What values of x is this function continuous? If you're stuck already, think about this. What did the old pirate say a year after his 79th birthday? What did the old pirate say a year after his 79th birthday?
Oh, hi, matey.
Hey, matey! Very good. Very good, Chris. You got it. Yep. Okay, again, let's start on the inside here. We have cosine of x plus 1, that's the inside function. It's continuous over its domain. In fact, it's continuous where? All real numbers. The outside function is natural log of x. Is the natural log of x continuous for all real numbers? No, but it is continuous over its domain, which means once it started, it ain't going to stop. And what is its domain? 0 to infinity. Can we include 0? No. Okay, you can only take the log of what types of numbers? Positive. So you know the cosine of x plus 1, it's going to clear that. Its domain is all real numbers. But when it clears, it better be strictly positive if we're going to be able to take the natural log of it. So the thing that you're taking the natural log of, you can call it the argument. It's the argument of the log. And in general, like we did in pre-cal, to find the domain of a log function, all you have to do is take the argument and say it's got to be greater than 0. The only difference is we didn't do a problem quite this fun in pre-cal. Now, what are the only types of inequalities that we can solve algebraically? Linear. Very good. Is this a linear? No. So we solve it some other way, either by finding test values or just envisioning what the graph looks like. And I like that. Cosine of x plus 1. What does the plus 1 do to the graph of chala? Shifts it up 1. Good. So you can actually sketch it. This will be fun. This will review chala. It's going to go up to 1, down to negative 1. And we're going to have 2 pi here. There's pi. And then pi halves. And 3 pi halves. That's on that side. And then we're going to have the same marks over here. And there you go. So as you're sketching this, with notability, try to sketch it all with one smooth, continuous line. So it's going to look something like this. Oh, I didn't do it. Oh, sorry. So there's 2 cycles. Now, of course, the plus 1 is cool with notability because with one line, you could lasso it on the end and do well with it. Shift it up 1 unit, right? So something like that. And now we can answer the question graphically. We want to know the values of x for which it is strictly greater than 0. And it's going to be everywhere except what? Where it is 0, right? Pi. The next one would be at, not at 2 pi because that's a high, 3 pi, and then at 5 pi, and then going backwards, negative pi, negative 3 pi. So at all the odd pi's, right? At all the odd pi's. Hey, speaking of odd pi's, it's Comal County Fair Week. So you ever go and you look at all the submitted foods? There's some really odd pies in there. There are some odd pies that are so odd they're actually cakes. And then by the end of the week, they all have mold growing on them, which makes them even odder. Okay. Comal County Fair. Apparently, no school on Friday. Cool. So you can go look at all the odd pies / cakes. Anyway, how do we list then where this is continuous if it's infinitely many values? You want to list them?
You do x not equal pi plus 2 pi n.
There you go. There you go. Let's go and answer the question. H is continuous. H is continuous. We don't have to explicitly say what the domain is. We can just kind of answer the question. H is continuous for all x. So there's that upside down A again. For all x not equal to. And the way you do it is, again, you pick your favorite occurrence of one of the taboo values. We got negative pi, pi, and 3 pi. I think pi is probably a nice one. And then it's just integer multiples of how often they occur. And, of course, they're 2 pi away. So you say can equal pi plus 2 pi n. And then you throw this in at the end where n belongs to what family of numbers? You don't want to do all reals because I can let n equal 1.5 then. And then we're counting by, it has to be an integer. Yeah, to make sure that they're whole numbers plus or minus. Okay. So now when n is 0, of course, you get pi. When n is 1, you get 3 pi. When n is 2, you get 5 pi. When n is negative 1, you get pi minus 2 pi, which is negative pi. So that right there takes care of all of them. We did that a lot last year with vertical asymptotes when we studied trig because, Anthony, as you said, tangent, cotangent, secant, cosecant kind of have a similar behavior with their vertical asymptotes. Okay. Cool. So now that we know how to find domains and where functions are continuous, let's see what else we could do. The continuity of functions play a very important role in determining graphics and their consequences. And here is the first important theorem that relies on continuity for it to happen. Okay, there's going to be 3 VT theorems this year. This is the first of the 3. And as with any theorem, you have to know the theorem itself, meaning you have to know the if part, which is the hypothesis. You have to know the consequence, which is the then part. And you also have to know how to formulate an argument using the theorem with the right justification. Remember, like the squeeze theorem? Oh, remember the squeeze theorem? There were like all those things we had to do to prove it. You had to find the limit of the 2 functions on either side. Then if they were the same, we had to state the inequality. Then we had to say then the limit equals that. All 3 of those things. Ugh, bother. Same thing here. So this one is called the intermediate value theorem, or the IVT for short. And you can refer to it as the IVT. But it does mean intermediate value theorem. So what does intermediate mean? Intermediate. In between, right? So it's the in-between value. And what kind of values do you think we're working with here? The in-between, we're actually going to be dealing with in-between y values. So in-between y value theorem, and theorem, of course, means law. It's the law. So it's the in-between y value law. That's another way to paraphrase it. But it sounds better as the intermediate value theorem. So let's read it. It says, if a function, f of x, is continuous on a closed interval from a to b. That's it. That's all we need. We need some function that's continuous on a closed interval. If that is all we have, then look at what bold claim we can make. Then every single time, then we can say that the function f will take on every possible value between f of a and f of b on that interval from a to b. Now, what are f of a and f of b? Those are the y values at the endpoints, right? That's all it is. So the y values at the endpoints. So let's kind of paraphrase that. F of a could be here, and f of b could be here. One could be higher than the other, or they could be the same height. We don't know. But basically, if we have one that starts here at this y value, and the other one ends over here at this y value, if we go from this y value over here to this y value through a continuum, guess what we must pass through along the way from one y value to the next? Every single y value in between them, right? Guaranteed at least once. Now, it could be that we travel through the y value more than once, because it could be like sine and it oscillates, or it could be that it goes way up high above and way down low below the other. We wouldn't know that for sure. But what we do know is there's no way to get from this point to this point without traveling through everything in between along a continuum, right? That's what it means. It's kind of a no-duh theorem, right? I can't get from here to the door, from right here to the door, without passing through every possible spot between there and the door, right? Because what would be the alternative? What did you say? Teleportation. Yes. I can't teleport from here to there. There's no wormhole I can travel in. I have to travel through a continuum from here to there. Okay? Which now we can answer finally the question. Finally we can answer the question. Why did the chicken cross the road? It had to cross the road. It had to. Because it couldn't teleport to the other side. That's the answer. Why did the chicken cross the road? What were the other options? Teleportation? No. The chicken had no other choice to get to the other side but to cross it. There you go. You heard it here first. Now, put it a little bit differently. Here's another way we could say it. If we know that we have a function like this in blue, okay, and we have the left endpoint being A and the right endpoint being B, notice the blue dots are f of A and f of B. In this case, f of A is lower than f of B. I highlighted the vertical range in between f of A and f of B. If I arbitrarily pick a random y value between f of A and f of B, call it y equals u, then the theorem will guarantee at least one x value that falls strictly between A and B that will generate that y value. Okay? Now notice if I drop this red line, it'll intersect the graph more than once, and that would give you 3x values. But we're guaranteed an x value on the interval between A and B that'll generate the y value. Notice this one also dips outside that interval. That's great, but it's not a guarantee. It doesn't necessarily have to happen. But what we do know is it can't get from this bottom blue dot to the upper blue dot without passing through every y value in between. Okay, so it's kind of a no-duh theorem, right? Kind of a no. We don't think in terms of teleportation. When we have to go somewhere, we know that we have to travel between here and there and every point in between, right? It doesn't even really phase us. So this is a no-duh theorem. Okay, let's go ahead and look at this nice example. Let's say that you are measuring the outdoor temperature on your back porch. I'm so ready for this weather. To be 47 degrees Fahrenheit. Oh, I can feel it. That feels so nice. Can y'all feel that? 47 degrees Fahrenheit. One morning at 8:15. Love it, love it, love it. Then you measure the temperature again at the exact same spot 4 hours later. If you're me, you probably haven't even left. You're still there, enjoying it. And look, it has now risen to 62 degrees, but you know, it's 62 degrees, although it's not 47, still pretty downright comfortable, right? Better than the 96, 97 degree temperature we had the last 2 days with like 99% humidity. All right, come on, fall. Explain why there has to be a time between 8:15 a.m. when you took the first reading at 47 to 12:15 p.m. 4 hours later, where the temperature on your back porch on that very same day had to be exactly in punto 51.351 degrees Fahrenheit. Anyone want to convince me?
Intermediate value theorem.
Exclamation point? Exclamation point. Could you elaborate on that?
It had to go from 62 to 47. 47 to 62 continuously jump from one temperature to the next.
Yeah, and so why does that mean it had to equal 51.351?
Continuous, and it would have to every value.
And where's 51.351 in relation to 47 and 62? It's in between. Or it's an intermediate value, right? Very good. Yeah, temperatures can rise very, very quickly. You can have temperature spikes, yes? But even with the temperature spike, it increases rapidly or decreases rapidly, but still through a continuum. Yeah. Okay, so that's why continuous functions are so important. So yeah, so it would be something like this. Since temperatures increase or / decrease through a continuum. That's a cool word. There's two U's back to back. Comma. And since we can do this, 51.351 is less than or equal to 62, which is less than or greater than or equal to 47. So kind of like the squeeze theorem, the inequality is a pretty important thing, because it basically says the value that we're trying to prove existed falls between the other two y values at the endpoints, okay? And since the one we're looking for falls between there, comma, by the IVT, and then you can reuse the phrasing from the question. There is a time between 8:15 and 12:15 where the temperature was 51.351 degrees Fahrenheit. Okay, it's a lot of writing. But there it is. So what are the essential parts of using the IVT? Number one, it's got to be continuous on the closed interval. Did we say that? Yeah, we said it was continuous. We implied it there everywhere. Number two, you have to show the inequality. The y value you're trying to prove has to fall between the y value points. We said that. Then you're going to invoke the name IVT, and then all you're going to do after that is reuse kind of the phrasing from the question. There is a time. Time would be the x-axis here. And that's what the theorem really proves, is that there's an x value that generates any given y value. Now, based upon that, would you be able to tell me exactly what time between 8:15 and 12:15 it reached 51.351? You'd have no idea. And it could have reached that temperature more than once, right? Could have gone up, come back down. So what the IVT is it's an existence theorem. It tells us whether or not something exists without necessarily telling us where it exists, just that it actually does. So an existence theorem. Continuous on a close. Y values are hemming in the value we want. And one more joke. What is a pirate's favorite appetizer? Escargot. 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 I did that same thing earlier. What is escargot? Snails. Snails. But you know what? This is funny. Snails are rich in vitamin C. And so naturally it'd be their favorite appetizer because it fends off the scurvy. Scurvy is vitamin C deficiency. And you got that aboard ships quite a bit. So, yeah. Oh, darn. Okay, yeah. All right. Alrighty then. Let's move on. Yeah. Okay. Any questions on example 5? Example 6. Okay. Theorems like the IVT, blah, blah, existence theorems, blah, blah, blah. Okay, so what we're going to do on example 6 is have some piecewise fun. We're not going to use the IVT. We are just going to practice whether or not the IVT applies on a given interval for a given function, which means we're going to be testing the hypothesis of the theorem, which is the if part, and I forgot what it says. So can anyone tell me what the if part of the IVT says? I'll start you off. If, that's all I know. On a closed interval. Good, from A to B on a closed, that's all we need, right? So really, all we're doing is checking to see then on these given closed intervals if this piecewise function is continuous, okay? Easy enough? Easy enough, okay. Let's take inventory real quickly of the piecewise function. It's part line, which is continuous everywhere. It's defined. Parabola, continuous everywhere, it's defined. Square root of x, continuous everywhere, it's defined, greater than or equal to 0. And 6 over 5 minus x, not continuous where? At 5. We have a what there, VA or a whole? A VA, non-zero over 0, okay? Now that may not even come into play, only if we're using that piece to the right of 5, which we are. So we have a built-in discontinuity right there. All right, so the other places where it may not be continuous is at the x values where it's handing off the baton from one to the other. Remember that? So this is a great way for me to get you back into the 3-step definition of continuity on the next test. But now instead of just saying test for continuity, I'm going to say does the IVT apply? And you're going to have to know to check for continuity. All right, so let's just do maybe 1 or 2 of these together because then the bell's going to catch us. It always ends too soon. I agree. From -4 to -2, is the function here continuous? Does the IVT apply? Why? All those values exist, and for that interval, we are staying exclusively on the top piece, aren't we? Which is a line. Because the equal sign is there, we know a line is continuous everywhere, so this one's yes. So if you had to answer it, complete sentence, yes. That's the affirmative. And then the justification will be since f is continuous. Where? In France? No, on the interval from -4 to -2. Now, when you answer it like that, that is showing that you understand what's required for it to apply. Continuous on that closed interval. All right, we got time for one more. -3 to 0. Well, I don't know. -3 is going to start on the top piece. So it's going to be continuous from -3 up to -2, because that's the line. And then it's going to jump to the parabola. So from -2 to 0, it's going to be continuous because it's a parabola. We do need to check at -2, though, don't we? So here is where I would say, like, justify and show your analysis on a free response. You have to go through the 3-step definition of continuity with proper notation. But right now, let's just do it informally. What's the limit from the left? Plug in your -2, you get 5. That's also the function value. So there's 2 of the 3 already. What's the limit from the right in -2? 5. Does 5 equal 5 equal 5? Yes. So is it continuous from -3 to 0? Yes. All right, we'll pick up there tomorrow at 6C.
Well, because look, it's asking from -3 to 0, and x squared plus it's from -2.
0 is going to be in the middle or in between -2 and 1. So it should be fine from -2 to 0, and it should be fine from -3 to -2. We just need to check at -2. And since they were the same, it worked. All right, have a great afternoon.